This is the continuation of the fourth lecture, and this section deals with another example of unconfined aquifer with recharge from rainfall. We are going to make a general equation for this condition. We consider this unconfined aquifer like this. Here what's the ground surface? What may be here? This level is H0. This level is H10 because this length, and from here to L. Now we have rainfall Q, intensity Q. We are going to find a general equation for this condition. So that we can do the same steps. We can consider an element like this, element of the aquifer at distance from the first plane here, x here, the delta x, height of this is single x, variable, and we can consider the inflow and outflow for this. Inflow is equal to Q, outflow is Q plus dq dx given delta x. Now we can write a mass balance equation. That is basically inflow minus outflow is equal to rate of change of storage. Here the rate of change of storage is equal to 0 because we are going to consider the steady state conditions. Inflow is Q plus, but there is rainfall here coming in Q. So this plus Q into delta x into 1. Running the depth into the board here is inflow. Outflow is Q plus dq dx delta x. That is outflow. For the outflow is equal to 0 now. Under steady state conditions it is 0. Now you can simplify this. Q minus Q is cancelling out, and you can remain with Q into delta x. This delta x. So this cutting with this one. This delta x cutting with this one. You can remain with Q minus dq dx is equal to 0. That is the simplified equation for that. And you can put this as dq dx is equal to minus q. Putting that way. Now you can apply the Darcy's law. Apply Darcy's law to Q. I put it as d by dx of minus kh dh dx is equal to minus q. That is applied Darcy's law. I write it here. D by dx of minus kh dh dx is equal to minus q. I am taking that there. Now integrate once. For integrating once, it becomes minus kh dh dx is equal to minus qx plus c1. One constant coming in there. So that you can divide this one now. H into dh dx equal to minus q divided by k x plus c1. I make a small change here. This is minus this side. So multiply throughout by minus, this will plus. You can make this also multiplied by minus, it becomes plus. So let this be constant to be plus c plus. Just let this be plus. then small change I make now. Because multiply throughout by 0, so multiply by negative sign here. So this negative sign cancelling out become positive. Negative again become positive here. And let this be positive one. Now integrate again. It becomes h square divided by 2 equal to minus qx square divided by 2x 2k plus c1x plus c2. That is the general equation. But the general equation are two constants c1 and c2. Two constants c1 and c2. We will find these two constants here now using boundary conditions. And boundary conditions are there is simple boundary condition when x equal to 0, h is equal to h naught. And when x equal to L, h equal to HL. Those are the boundary conditions, simple boundary conditions here. So you can apply them. So when x equal to 0, this becomes h naught divided by 2. This becomes 0, so that it becomes C2. C2 is equal to h naught square divided by 2. And therefore square divided by 2 is equal to minus qx square divided by 2k plus c1x plus h naught square divided by 2. That will be the first boundary condition. When for the second boundary condition, when x equal to L, HL square divided by 2 is equal to minus q h squared by 2k c1L plus h naught square divided by 2. Yeah, c1 is equal to c1 you can bring all the other terms aside. 1 upon L times c1 is equal to 1 upon L times HL square divided by 2 plus QL square divided by 2k plus h naught square divided by 2. Substitute that in the equation here. I can now find the general equation. And write it here like this. Write the general equation with the boundary conditions written. H naught square divided by 2 is equal to minus qx square divided by 2k. But C1 is equal to this part 1 upon 2L H squared plus QL squared then by K minus H naught squared X L. And that is C1 plus h naught square divided by 2. So this is the general equation. General equation for the aquifer. This is the one we have here right now. So we can use this to find the h ready point. So there is an expression for h square. So then you can make it h square is equal to you can make an expression for you can remove this 2 by multiplying throughout by 2. H square is equal to minus qx square divided by k 1 upon L times h square plus ql square divided by k L plus h naught square. That is square. Now H is equal to H will be equal to square root of this. H is equal to square root of whole thing here. Minus Q X square divided by A. That is the general equation for H. So if you know the value of X and all these terms, you can find out H. Right. Now that is the, I'm not going to do any problem like this, so that if you get a problem like this, you can put these values and find out H at certain point X. Right. With this, I shall end the fourth lecture on groundwater flow. Thank you very much.